Hello everyone, I'm Mehmet Öncankaya and today I will be talking about vector spaces and their applications in signal processing. First of all, vector spaces are the sets of vectors along with a field that is closed under vector addition and scalar multiplication. And the functions, the signals can be considered as a vector, and so vector spaces are useful since the study of vector spaces is actually the study of signals. And as subspace is a subset of vector space, again closed under multiplication and vector addition, and it's useful since we can project a signal onto a desired subspace. And for example, if we have a measurement vector of the output of an LTI system with some noise, we can clean that noise if we know the subspace of the possible outputs of that LTI system. And the clean measurement is actually the projection of that measurement vector onto that subspace. And again, similarly, we can use this concept for dimensionality reduction in signal processing. Now let's move on to basis. And basis is a set of vectors in a vector space that spans that vector space and that are linearly independent. Their elements must be linearly independent. So any vector in that vector space can be written as a linear combination of the vectors in that basis. And basis is a useful concept since we can represent a signal in different bases. For example, we can investigate the frequency component of a discrete signal using DFT basis, or we can use this concept to image compression. For example, JPEG compression uses DCT basis and compress the image by only selecting some of the DCT coefficients rather than all of them. So it's all very useful, as you can see. And norms provide a way to measure the length of a vector or distance between two vectors or two signals. For example, a problem of data representation of audio information quantization, it may be appropriate to use a norm for which a representation is chosen that is best as perceived by human listeners, or different norms can be used in different applications. For example, similar thing can be applied to norm used for video coding. We can choose a norm for human perception, and also we can use different norms in high-speed applications. For example, if we have a hardware that computes absolute value easily rather than square, we can use a L1 norm, for example. And using the properties of the norm, we can find the minimum norm solution. Finding the minimum norm solution is very important since this problem occurs in important applications like tomography. In tomography, our aim is to reconstruct the 3D cross-sectional density fxy using the measurements which are the set of line integrals of that density. For example, if this is our patient, we radiate for example X-ray like this, and we measure the intensities here, and then we can reconstruct the patient's body tissues using these measurements. And in its very simple form, we can consider this problem. For example, if we have a matrix like this, 3 by 3 matrix, consider this as a patient, and if we have a measurement along the diagonal, anti-diagonal, and center column and row, we can reconstruct the matrix optimally using minimum norm solution. But normally we can reconstruct the matrix, of course, since we have 4 measurements but 9 unknowns. But we can again reconstruct the matrix using minimum norm solution. So this is very useful, and similar problems also arises for other inverse problems. An inner product can be used for projection operation. For example, least squares or minimum mean squares filtering or estimation use inner product techniques, and it can also use for optimization. For example, and to illustrate its usefulness, the usefulness of the norm and inner product, more specifically, we can consider the approximation problem. So the problem is that we want to find the x set such that the approximation error E is small as possible. Geometrically, we can see that error is perpendicular to P1, our subspace basis, when the error is minimized. And we can use the inner product operation for this to find the optimal approximation. And we can generalize this concept to higher dimensions or other spaces using the generality power of the concepts. And approximation is very important since they are always occur in signal processing. For example, for finding a FRI filter as an approximation of ideal low-pass filter, we can use the approximation problem solution. So that clearly illustrates the importance of them. So that's all. Thanks.